All right, folks, let's talk about climate change. All right, so first I want to define a few terms here. You see a couple here that are very important to understand. First, we have the greenhouse effect, which is basically just this phenomenon that whereby these gases in the atmosphere uh, cause the Earth to be warmer, or the surface of the Earth to be warmer than it would otherwise. Okay, so I'll explain this in more detail in a minute, but basically the greenhouse effect is this generic term for the process um, whereby these greenhouse gases absorb heat and make the Earth a little warmer than it otherwise would be. The enhanced greenhouse effect. So the greenhouse effect itself is fine. In fact, it's a good thing. In fact, it actually makes life possible. Without the greenhouse effect, life on Earth, as we know it, would not be possible. It would be anywhere from 50, 60 degrees colder on average. Okay, so liquid water couldn't exist. Um, and so we would not have life as we know it. So that's the greenhouse effect. The enhanced greenhouse effect, that's the part that we're worried about. We're worried that humans are causing the greenhouse effect to become a little stronger, which is causing the Earth to warm excessively. A greenhouse gas is just a gas that absorbs infrared radiation, and it's invisible to shortwave radiation. Okay, we'll talk about that in a minute. Anthropogenic is just a generic term that means caused by humans. So you can have anthropogenic anything. Anthropogenic climate change is one way that that term is used. And as you might guess, since anthropogenic means caused by humans, anthropogenic climate change is the component of climate change that is believed to be caused by humans. Okay. So let's go over the greenhouse effect. This was covered in your video, so if you haven't had a chance to watch it, I strongly suggest you do so. It's a very illustrative and easy to understand video. But basically, this is how the greenhouse effect works. Okay, so you have the surface of the Earth, okay? You have this atmosphere here. There are greenhouse gases in the atmosphere, including carbon dioxide, methane, water vapor, and some other ones that we'll go over in a minute. So these gases are kind of dispersed throughout the atmosphere, all throughout the atmosphere. All right, so sunlight comes in to the atmosphere. The sunlight itself is shortwave radiation, or it's primarily shortwave radiation, okay? Um, So shortwave just refers to the fact that the wavelengths are really short. It's sort of the more powerful radiation like ultraviolet and visible spectrum and all that stuff. We're not going to get a whole lot of detail, but I do want you to remember what shortwave radiation means. And shortwave radiation is the primary type of radiation that comes from the sun. Okay, this is what keeps the Earth warm. Well, this is what gives the Earth heat, the sun. Okay, so it's almost entirely shortwave radiation. So the key to the greenhouse effect, or the first key to it, is that this shortwave radiation is able to pass right through all these greenhouse gases without being absorbed or reflected. Okay, some of it is reflected and absorbed by other gases in the atmosphere, but the greenhouse gases themselves do not absorb or otherwise interact with the shortwave radiation. Okay, now about when this sunlight reaches the Earth, more than half of it goes through the atmosphere, including through the greenhouse gases, reaches the surface of the Earth. Okay, about half of that radiation is absorbed by things on or near the surface of the Earth. Okay, so shortwave radiation comes in, passes through the atmosphere for the most part, right through the greenhouse gases. Now, when it's absorbed by something on or near the Earth's surface, like a building, like a road, like a tree, you step outside and your skin, when your skin gets warm when you step outside, it's because your body is actually absorbing the shortwave radiation and it's warming up your skin. Now, what happens after something absorbs shortwave radiation is that it re-emits a lot of that radiation back out. Okay, now the type of radiation that it radiates back out is primarily long wave radiation. Okay, so very important, long wave radiation. So if it's absorbed, it is converted to long wave radiation. Now some of this long wave radiation passes through the atmosphere and goes right out to space. A lot of this, okay, is actually absorbed by the greenhouse gases um, on its way back out. So this is the fundamental principle here. Shortwave radiation from the sun, invisible for the most part to greenhouse gases. If it gets absorbed by something, it becomes long wave radiation when it comes back out. Now the long wave radiation can be absorbed by the greenhouse gases. You see the layer here. And then if it's absorbed by the greenhouse gases, it's going to re-radiate in all directions. Okay, and just by virtue of the law of averages, about half of it's going to go back toward the surface of the Earth. And so instead of this heat escaping through the atmosphere, it's absorbed and pushed back or re-radiated back toward the surface of the Earth. That's how greenhouse gases keep the planet warmer than it would be otherwise. Okay, so remember, the greenhouse effect itself is something that makes life possible. It's been around way before humans even got here. So the greenhouse effect is a very important process. One other thing I want to point out is that if the shortwave comes in, if it's reflected, okay, if it's reflected off of a surface, like a light colored surface, like I don't know, a light colored sidewalk or a patch of ice or snow or whatever. So if it's reflected, not absorbed, reflected, it actually stays shortwave radiation and it bounces right back through the greenhouse gases and the atmosphere in general. Okay, so if it reflected, it just bounces right through. If it's absorbed, it's re-radiated back out, and the greenhouse gases then absorb it. Okay, so this is the fundamental principle of the greenhouse gas. So this is what I'm considering fact number one about climate change. The first fact about climate change is that we know that greenhouse gases trap heat in the atmosphere. Okay, this is not open for debate. This is settled science. Even people that deny that humans are impacting the climate understand that greenhouse gases trap heat in the atmosphere and in fact make life possible. Okay, so keep that in mind. That's fact number one. So let's go over some greenhouse gases. There are a number of greenhouse gases. I'm not going to get into a lot of detail. Here are the primary ones here. The two that we're going to focus on the most are carbon dioxide, and if you remember, CH4 is methane, okay, which is over here. So this chart actually shows the concentration of the red line is carbon dioxide, the black is nitrous oxide, and the blue is methane. So this is your year, okay, so the year, well, there's year 0, but year 1, all right, so AD or the Common Era, so up through about 2010. So these lines show you the concentration, okay, of these gases in the atmosphere throughout time. And you can see, let's follow carbon dioxide, the red line. If you follow it through time, it's pretty stable. It goes up and down, a little bit up, a little bit down, right? And then you notice a very distinct trend. Right around the late 1800s, late 1700s, early 1800s, you notice a sharp increase, okay? Shoots right up. Very unnatural, very much not a coincidence. So if you know your history, the history of Western society around the late 1700s, early 1800s, that was the time of the Industrial Revolution, so we started using a lot more fossil fuels, which we have discussed previously in class. Okay, so this increase in carbon dioxide is a direct reflection primarily of the increased use of fossil fuels. Methane is about the same, it increased around the same time, but a little bit sooner. That also has to do with livestock production as well. So those are the main two that we're going to worry about. So just a term here, concentration just refers to the sort of the amount. I mean, really it's the percent of the atmosphere that's of a specific gas, but you can think of it as the amount. So a higher concentration means more of that gas in the atmosphere. Okay, so another thing that I want you to understand is that greenhouse gases, once they go up into the atmosphere, they're generally distributed evenly throughout the world, okay? So it's not like, the US emits a lot and there's extra CO2 above the US's atmosphere, in the US's atmosphere. That's true to an extent, but for all intents and purposes, when you emit, it's just considered global because it spaces out. Some other important points that I'm not going to get into in a lot of detail, but I just want to bring it to your attention. Parts per million is how most of these are measured. That's the concentration. Global warming potential. Briefly, global warming potential is the relative impact of a greenhouse gas over a 100-year period. And it involves the potency. So some gases are really good at absorbing heat, and some last a long time in the atmosphere. So if you have a very potent gas that lasts a long time in the atmosphere, it's going to have a high global warming potential. In other words, it's going to really impact the climate more so than something that is either not very potent or has a shorter lifetime. I'm not going to worry about that. You don't need to know that, but I just want to put that out there. But what I do want to mention, because we have talked about this before, is that methane, as we've mentioned before, is a lot more powerful or potent than carbon dioxide in terms of trapping heat. If you remember, we discussed methane is about 25 to 30 times more potent than carbon dioxide. Really what that refers to is this global warming potential. And so all this means is that if you emit an equivalent amount of methane and carbon dioxide, the methane is going to have about 30 times more impact on the climate than the same amount of carbon dioxide. That's really what it means. So I just wanted to bring that to your attention. So what I do also want to ask is, if methane is so powerful, why are we so worried about CO2? If you think about that for a second, I believe that was in your reading, but here's why we're worried about CO2. If you look at, so this chart on the right is the global greenhouse gas emissions by gas. On the left is the US greenhouse emissions by gas. What jumps out to you at this chart right away should be that, drum roll, carbon dioxide is by far the biggest source of greenhouse gases that we have both in the world. If you add this carbon dioxide to this carbon dioxide, you get about 76% and 81%. So this includes the impact of the global warming potential. So in other words, about 80% of the impact that we think we're having on the climate in the US is from carbon dioxide, and about 76 to 80% of the global impact on the climate is coming from carbon dioxide. So that's why carbon dioxide is the one that you hear the most about. It's the one that we emit way more of, even though it is less potent than methane. And to help you understand why our CO2 emissions are so important, I want you to think about the carbon cycle. Now, the carbon cycle is something that I'm sure you've learned about at some point in your life, probably even in elementary school. So the carbon cycle, and this is, sort of a generic illustration of it, but it does give you a good idea of some of the different aspects or elements of the carbon cycle. So the carbon cycle just refers to the fact that carbon dioxide is constantly cycling all over the planet, okay? And so you can see in this illustration, you have things like trees that pull in CO2 out of the atmosphere. The ocean actually absorbs a lot of the CO2 that's in the atmosphere, but then the ocean also releases it to the atmosphere. When you have vegetation or plant life that's burned, it releases carbon dioxide, but then when the plant life grows, it's pulling in carbon dioxide. The plants, they naturally biodegrade and they're releasing CO2. You have soils that are storing CO2 and releasing it. Okay, so the CO2 is constantly cycling in and out all the time. It has been since, 4 billion plus years ago when the Earth was formed. Okay, so much so that the natural emissions are about 770. Hopefully you noticed that term. So that's gigatons or billion tons. So the natural emissions, if you add all this up, are approximately, and I don't want you to focus on this number at all because this is a ballpark number. It's not meant to be taken as an exact. But I do want you to understand it's pretty big, 770 billion tons of CO2. But the humans, through primarily fossil fuels, according to the IPCC, only add about 29 billion tons per year. So think about that. Naturally, the Earth emits about 770 billion tons. Humans only add about 29 billion tons per year. So you think about it, the natural emissions are way, way bigger than human emissions. So why then are we worried about human emissions? Okay, so think about that and press pause, and maybe you can kind of think about why that might be the case. So as it turns out, the reason that we care is because humans are throwing the natural carbon cycle out of balance, okay? So the Earth is naturally able, effectively, to balance the amount of CO2 emissions. So if you look back to this chart that we looked at earlier, so through the last 2,000 years, yes, it fluctuates a little bit looking at our carbon dioxide. So it goes up, goes down, goes up, goes down. But by and large, the concentration of greenhouse gases in the atmosphere, carbon dioxide in particular, remain pretty constant, even though at this point humans were actually in the picture. But once we started to emit all this CO2 around the time of the Industrial Revolution, we ended up throwing this carbon cycle out of balance. So even though you only add a little bit relative to what the Earth does, it's enough to throw it out of balance. And you can think about it, many analogies, but one I like to think of is weight, gaining weight. So let's say you're, you burn about 2,000 calories a day. Okay, so if you eat exactly 2,000 calories, you're not going to gain any weight. If you eat, an extra 100 calories each day, you're not going to gain weight really quickly, but you will slowly gain weight because as long as you continue to only process that 2,000 calories, that extra 100 calories is going to add up over time. And eventually, you'll end up overweight. There's nothing you can do about it. I mean, that's if you don't burn the calories, then it's going to end up with excess weight. What's a similar phenomenon here is that we're overriding, overstretching the Earth's ability to absorb these greenhouse gases. Okay, so in terms of where these emissions are coming from, this chart on the right is the U.S. carbon dioxide emissions by source, pretty similar to global. But I want you to press pause and think about um, what is actually releasing these carbon dioxide emissions in each of these sectors. Okay, so we have the electricity sector, which is fossil fuels, right? So burning fossil fuels, that's going to generate your CO2. Transportation, we're burning oil to generate our carbon dioxide. Industry, we're burning fossil fuels, coal, oil, natural gas to power factories and so forth. Residential and commercial, we're burning fossil fuels, okay? So the only this small little 6% is not due to fossil fuel combustion, all right? So in other words, the best way to reduce emissions is to reduce fossil fuel use, okay? So fossil fuel use is the primary culprit of CO2 emissions, all right? And these are just some possible strategies to reduce emissions. We'll talk about some of these in this class, especially energy efficiency, conservation, and we'll do renewable energy as well. So a lot of these things are ways that we can reduce our emissions. But the thing I really want you to remember is that the best way to reduce emissions is to reduce your fossil fuel use, okay? So fact number 2, we already know the greenhouse gases trap heat in the atmosphere. The second fact is that we know that humans are causing concentrations of greenhouse gases to increase. Again, not open for debate, number 1, not open for debate, number 2. We also know that the number 1 anthropogenic source of greenhouse gases is energy use, okay? Again, really not open for debate. Okay, so let's look at another kind of sign that maybe we should be concerned here. If you look at this chart, shows the temperature anomalies since 1880. So we've been measuring temperature directly since 1880, so over 100 years. And what this chart is telling you, if you know your time on the x-axis, and this is your anomaly. So if you would take all of these are annual average temperatures across the surface of the Earth. So if you took all of these and you averaged them together, that would be this line right here. Okay, so if you took all of them through here, you averaged them, that would be your line. And so if the data the datum is below the line, that means at that year it was below the overall average temperature. Okay, so you can see through here, it was below the average temperature, you know, until the like mid 1940s or mid 1900s, excuse me, or so. You know, of course, there's fluctuations. This is not going to be a smooth curve. But overall, there's a clear trend, especially starting in the 1970s or so, that it's been significantly warming over time. And remember, this is only relative to average. So really overall, I mean, the line is generally going up over time. And if you look, it's effectively the same data. Sorry about that here. Okay, so this is effectively the same data. Again, below average for most of the first 60 or so years, and then above average. But if you drew a line to kind of fit that data, it's showing you that the temperature is increasing. So we know the temperature is increasing over time. There's a minor argument against this, but it's really just a fringe argument that basically is very hard to prove. Okay, so if you look at the hottest years on record, okay, here are the 16 hottest years on record. So, you know, number 1 through 15, because they're a bunch of ties. And then if you look at the year, and then this is the anomaly, what do you notice about this chart? Go ahead and press pause. What do you notice about this chart? So hopefully you notice that the years, the hottest 15 of the hottest 16 years ever recorded are since 2001. Okay, so it's getting pretty hot. And the only other one is 1998. 2016 is on pace to be even hotter than 2015. So again, the trend is really abundantly clear. Now, you have to be careful. There is, you know, it's possible, you know, we're dealing with 20-year timescales, 30-year timescales. Anomalies can happen, so we're not 100% certain all of this is due to anthropogenic climate change. But again, signs are really pointing to that being the case. And this illustration just shows you the average change in overall surface temperature since 1900. And the red means it's hotter than average, and the blue means colder than average. White means no data. You can see really everywhere except some parts of northern Canada and a little bit of South America and Russia and so forth. It's getting hotter. Okay, so fact number 3 is effectively we know that the climate is warming. I mean, all signs point to the climate warming. Okay. All right, so if you think about just these 3 things alone, we know the greenhouse gases trap heat in the atmosphere. We know that humans are causing these concentrations to rise. So that in itself is probably enough to say, well, maybe we should think about doing something about these emissions. But also we look at the fact that the climate is warming. So we have these two facts that are saying, well, maybe we should think about doing something. And then we throw in there that the climate is warming. Okay, so maybe we should be thinking about doing something. Another aspect of this is that if you look at the potential impacts, now these are all over the map. It just depends on the region of the world and the time and all that. There's other factors that are involved. But generally speaking, the impacts are going to be all over the place. Okay, so there's going to be all over the world. Generally speaking, they're going to be bad. Okay, so if you look at rain and flooding, droughts, hurricanes, diseases, species loss, all kinds of stuff. All right, mostly bad. And so according to the Intergovernmental Panel on Climate Change, which is the most respected body on climate change research in the world, if you read this quote, taken as a whole, the range of published evidence indicates that the net damage costs of climate change are likely to be significant and increase over time. That's really just a fancy way of saying it's probably going to be bad and it's only going to get worse. Probably going to be bad and will only get worse, okay? So our fourth fact is that if climate change continues to happen, the results will almost certainly be catastrophic. Very little to argue there. There is some benefits, you'll have longer growing season, you might have more plant growth, so that's helpful, but overall, on balance, not going to be good. And the last little part is if you look at the folks that are doing research on climate change, okay? So this quote I think is pretty telling. The multiple studies published in peer-reviewed scientific journals showed that 97% or more of actively publishing climate scientists agree that climate warming trends over the past century are extremely likely due to human activities. So basically what that means is you have these folks that are doing the top of the line research about climate change and what's influencing it. And overall, it's overwhelmingly agreed upon by people that are trained professionals in this field. Overwhelming majority say, it's almost certainly the humans that are causing these climate change, this climate change evidence that we're seeing. So they're saying, look, we see this evidence. We're looking at everything we know about all of this stuff about greenhouse gases and climate change and the greenhouse effect and all this, and we're really, really, really almost certain that humans are the ones causing this. Okay. And you could go group after group after group. I mean, here's a list of 200 worldwide scientific societies. We have all these folks. These are professional scientific societies whose job is to perform scientific research and publish scientific data. And they're all saying, if you read these quotes, we need to do something about it. We're almost certain that humans are causing it, okay? So the last fact, and this should be fact 5, and I apologize about that. We know the greenhouse gases are there. We know that we're increasing them. The climate is warming. We know it's going to be bad, or almost certain it's going to be bad. And finally, there is really broad consensus that climate change is probably being caused by humans. Okay? So a real quick summary of our 5 facts. Summary, greenhouse effect, settled science. We know it. Okay? Humans are increasing the concentrations in the atmosphere, mostly through fossil fuel use. The climate is getting warmer. Anthropogenic climate change, global warming, will be really bad if it happens, and there's broad consensus that humans are at fault. So David McKay, who writes a book about energy use, has this quote. So I want you to read that quote and think about how that is analogous to climate change, and I'll let you think about that. And the last little thing I want to throw in there is take a second to read this cartoon and see what you think the point is. Okay, if you think about what if we actually achieved what we need to achieve to reduce our fossil fuel emissions and other CO2 emissions to the point that we have headed off this problem of global warming, climate change, excuse me. If in the very small chance that these 97% of scientists in the world are wrong, that all of these signs, these logical conclusions that we make are absolutely wrong, and we are dead wrong about climate change, humans have no influence whatsoever, okay? So just assume we figure out 50 years from now, you know what? We were wrong, my bad. If you think about the sort of fallout from that, the quote unquote fallout from that, if we do what we need to do to reduce and eliminate emissions, Think about society and how it will look. We'll have renewable energy all over the place. Get rid of all these big, dirty fossil fuel burning power plants. Get rid of all these dirty fossil fuel burning heating sources. The cars down the road, they're going to be mostly quiet. You're not going to have all these emissions. You're not going to have smog being formed. You're not going to have low-level ozone being formed. You're not going to have asthma attacks because of the stuff from tailpipe emissions. There'll be more, locally produced energy, so you'll have your own solar panels. You'll probably be able to provide yourself with electricity. So all of these impacts, okay, cleaner water, cleaner air, healthier cities, healthier countrysides, more power over your own energy source. Um, um, all of these things will probably happen if we do what we need to do to fight climate change. And so even if we're wrong, the world will almost certainly be a much better place just because we tried to address the problem. Okay, so those are the 5 facts and an additional 6th.